Nothing against musicals. Yeah, absolutely against like leaving.
What's my
I guess that's probably the easiest way. Don't invest in musicals.
Go to the musicals.
When you're like,
When you sit on this computer, we can stop that.
it's not against musicals. That's all I'm trying to say. Like, I don't know. Maybe that's what you're trying to say. Pretty sure that jacket is
Now in my mind,
it's big.
See, we divide this one by five, and this
I
goes
was
like
saying, you don't like it.
he has, and we go.
I don't know how it did that. No, you said, I don't know how it did that.
All right, on page 219, we're going to talk about this section that's called related rates. So if you think about the taco cart example, we had two rates. We had the 2 feet per second and the 5 feet per second, and somehow they were related to each other because those were walking rates. One was in sand, one was on the road. We're going to try to take a look, just for practice today, different equations of geometric shapes, and we're going to practice finding the derivative of these equations. What can be a little different is we have A's and R's and V's, sometimes trig functions. So we're going to be looking at different variables, but the derivative techniques or shortcuts don't change. What is, again, going to be a little bit different is we're going to implicitly differentiate these. Remember in the last section we just finished, every time we took the derivative of a y variable, we wrote dy over dx. We're going to do something similar here. The difference is we're going to implicitly differentiate these with respect to time. If you look at the rates from the taco cart example, do you notice how they are feet per second? Second is a time unit. When we find the derivative, instead of writing dy over dx for these rates, we're going to write d something over dt. Okay, with respect to time, just means what your kind of independent variable is representing in this case. So if we want the derivative of area, for instance, this would be dA over dt. If we want the derivative of a radius, this would be dr over dt. So it's a similar concept, just instead of dy over dx, we're now going to have d something over dt. So this first equation is the surface area of a sphere. We're just going to practice finding the derivative with respect to time. So if you want to take the derivative of a, that would be dA over dt. And then we're going to try to find the derivative of the right-hand side. How do you want to find, or what do you think the derivative is of 4 pi r squared?
I'm going to have to do some 1v2.
You are multiplying, but the 4 pi is a constant, right? It's not another variable, because pi is a number, right? If we bring the power down, that would make it 8 pi r, and the new power would be 1. But we just took the derivative of an r variable, so we're going to write dr over dt. Whatever variable you take the derivative of, it needs to have that derivative symbol with respect to time. So it was dA over dt for area, dr over dt for the radius. Now, if these are derivatives, these are representing specific rates of change. So dA over dt would be the rate of change of area. And then dr over dt is the rate of change of the radius. Maybe a good example for us to kind of think of is a balloon. Okay, if you are blowing up a balloon, clearly the surface area is changing and the radius is changing because the balloon's getting bigger, but the rate at which the area changes is different perhaps than the rate at which the radius changes. So we have these two different rates in this scenario that we're going to take note of. Okay, let's go ahead and try another one. So volume of a sphere. All of these are with respect to time. So the derivative of volume would be dV over dt. What about the right-hand side? We got to take the derivative of this r variable. Can we do a derivative shortcut? Four-thirds and pi are your constants. What do you think, Christian?
I'm thinking we go with the 3 in the top right and we multiply it by 4/3.
Okay, so it's going to be the power rule. So if we multiply the 3 down, that will actually cancel out with a 3 in the denominator. So we're left with a constant or a coefficient of 4 pi. We have a new power of 2, and we just took the derivative of a radius, so that'd be dr over dt. So what these derivative notations are representing is the rate of change of volume, and then the rate of change of the radius. Okay, derivative is a slope, it's a rate of change. In this case, it's specifically a rate of change of a property, radius, volume, whatever we're working with. All right, let's try one that's a little bit different. So we have this equation, kind of looks like the Pythagorean theorem a little bit, just rearranged. They're telling us that c is a constant. It is a number. So let's see if we can take our derivative all the way through. How do you want to write the derivative of a? dA over dt. All right. How are we going to find the derivative of the right-hand side? We got a chain. Good. All right, so we'll bring down the 1/2 from the root. We'll keep the inside, new power, negative 1/2. And how do we finish the chain rule? Multiply by the derivative of the inside. Okay, so the inside part, what's the derivative of c squared? C is a constant. 0. Because this is going to be a number, right? C is a constant. So the derivative of c is 0. And then we have to subtract the derivative of b squared. Now, they didn't say b was a constant, so this means b is actually a variable, something that could change. So that'd be negative 2b dB over dt. Now, if c wasn't a constant, we'd have to take that into consideration, but since it's a constant, the derivative is 0. So in terms of the rates, okay, the derivatives, we have the rate of change of A, whatever that is, and the rate of change of B. Probably the two sides of a triangle, okay, how those might be changing. We doing okay? It's a little different, but we're going to be doing a lot of these. Let's try 4. Volume of a cylinder, they're telling us that R is constant. Hopefully that makes sense, because if you think about a cylinder, the radius is always the same all the way through the cylinder, no matter what you have in it. Okay, so the radius doesn't change. Let's go ahead and try to find the volume. So, not volume, the derivative. Derivative of volume, dV over dt. Now, if R is a constant, meaning a number, it looks like the only variable we actually have to take the derivative of is h. So what might the derivative look like? This is where it gets a little tricky. We're going to need that. dH over dt. The question is, what else is there? Because the power on the h is 1, but you'd have to bring down that 1 and multiply it by the coefficients. Remember, r is a number. Okay, r is constant. So we'd be left with pi r squared. And the h would go away because the new power would be 0. But we still have that dH over dt because we took the derivative of an h variable. So in this case, we have the rate of change of volume, and then the rate of change of the height. All right, let's try a trig example. So in our triangle, the cosine ratio of our angle is the adjacent side over the hypotenuse, so we have x over 15. It might be beneficial for us to rewrite this a little bit. This is the same thing as 1/15 x. So maybe instead of writing it as a fraction, you can bring out the 15 as a coefficient. So let's try to practice writing our derivative. The derivative of cosine is negative sine theta. Now, what's the variable over here? Theta. So we need a d theta over dt. Then we got to take the derivative of 1/15 x, which would just be 1/15. But we took the derivative of an x variable with respect to time. So this would be dx over dt. So in terms of these rates, we have the rate of change of theta, okay, how that angle is changing. And then we have the rate of change of x, okay, how this side length is changing. All right, last one. Volume of a cone. They didn't specify at least that any of these are constant, so every variable is in fact a variable. Let's go ahead and take the derivative. So derivative of volume, dv over dt. How do you want to find the derivative of the right-hand side? If you read it out loud, maybe that'll help. We're multiplying. We have 1/3 pi r squared times h, because r is a variable and h is a variable, neither of which are constant, meaning a number. So if we're multiplying two variables together, we're going to have to go through our product rule. So let's go ahead and list the 1/3 pi r squared as the first function, and then h as our second. So we'll have 1, and then d2. The derivative of h could be dh over dt. And then we'll add 2 d1. So we'll have to bring down the power of 2, make it a 2/3 pi. New power would be 1. And we took the derivative of an r variable with respect to time, so dr over dt. So in this case, we actually have 3 rates, unlike the other ones where we had 2. So this would be rate of change of volume. This would be rate of change for height. And then rate of change for the radius. Are we doing okay with the derivatives? It's just something over dt now. It's a little different, okay? It's going to take us some time to get used to. We're going to go ahead after practicing these, okay, because we really could use any of these or even some other equations depending on the scenario we have. We're just going to go ahead and practice as many examples of these related rate word problems as we can, just so we can get comfortable. So on page 220, let's go ahead and take a look at this one. Air is leaking out of an inflated balloon, which they tell us is the shape of a sphere. Okay, so we have this like perfectly circular balloon. And air is leaking out of the balloon at this rate. Okay, 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, we're going to try to figure out the rate of change of the radius. So if you can visualize this, you have a big balloon and you're letting air leak out. Clearly the balloon is shrinking. So what's changing in terms of different aspects or properties of the balloon? If the balloon is shrinking, what's changing? Surface area, radius, volume. Okay, everything is decreasing because we're getting smaller. Okay, so let's think about some of the variables that are listed in this problem. And you actually said some of them right there. Let's see, we're dealing with a radius. Can we identify another variable that's perhaps mentioned but not mentioned exclusively? Are they hinting at another variable in there somewhere? Yeah?
Volume here says cubic centimeters.
Cubic. Okay, so a cubic unit is a volume. They're hinting at a volume variable. Now, it didn't say anything about the surface area of the balloon or a squared unit for area, so I think we'll be safe to say and not assume that is a part of this question. Now, we said that when this balloon is shrinking, clearly the radius is decreasing and so is the volume. So are any of these variables constant? No, because they're changing. All right, so we'll just write none. Let's go ahead and identify some of the rates, aka derivatives, that were given in this problem. Let's see, they give us the rate of 230 pi cubic centimeters per minute. Can we identify what that rate is representing? The rate of change of what? So d something over dt, what's that something?
Volume.
Volume, because it was a cubic unit. Now let me ask you this. If air is leaking out at this rate, what should this number be? Negative. Right? We said that volume was decreasing, so the derivative should be negative. Okay, so a little tricky there because they don't explicitly tell you it's negative, but the wording or the clues in the scenario should lead into that. Can we identify another rate, perhaps the one that we're trying to find? Rate of change of radius, so this would be dr over dt. All right, so again, if you visualize this, we have this big balloon. We're letting air out, so it's starting to shrink. And in that shrinking process, we are specifically interested in the rate at which the radius is changing, but specifically at this point in time. So when the radius is 4 centimeters, whenever that instance is, we want to know exactly how fast the radius is changing. So this is what I refer to sometimes as your point in time or your snapshot moment. If you were to take a picture of this balloon decreasing and you were to print out that picture, the radius of the balloon would be 4 centimeters. Okay, so your snapshot moment, your point in time, that would be something useful to identify. Now, can we think of an equation that can bring all of this information together? Kind of like how we did the Pythagorean theorem for the taco card example. Can we bring an equation that relates volume, radius, and this geometric sphere shape together? Probably. We had a few on the previous page. Those are common ones that we're going to use. You see it, Griffin?
Yeah, v equals 4/3 pi r cubed.
Okay, pi r cubed. So that's on the front. Typically, they'll give you an equation to use. If they don't, you can definitely reference that page to help you find an equation. So this is something good that can bring all of these variables and information together. Now, one thing we have to be clear on, okay, we're eventually going to take the derivative of this, but we have to do some checking first. Okay, does everything check out? Notice how in this equation we have a variable of v and r, and we said neither one of those is constant. So we're going to have to keep these as variables. We also need to make sure that for every variable we have in the equation, we have a rate associated with it, either a rate with a number or the rate that we're trying to find. So notice how we have v and r as variables, and we have dv and dr as our derivatives. You see how those are connected? Nothing's missing? We're good to go. Okay? So based off this equation, let's go ahead and take the derivative with respect to time. So derivative of volume would be dv over dt, and then derivative of the right-hand side, 4/3 and pi are your coefficients on the r. We'd have 4 pi r squared dr over dt. All right, so now that we took the derivative, let's kind of bring all this information together. Do we know the rate at which volume is changing? Yes, negative 230 pi. Do we know the radius at this specific moment in time that we are interested in? Do we know our snapshot moment radius? 4. Do we know dr over dt? No, because that's what we're trying to find. That was our question mark rate. Do you think you can solve for dr over dt? Probably. Negative 230 pi equals 4 squared is 16 times 4 is 64. So dr over dt equals negative 230 pi over 64 pi. Pi's would cancel. Can someone get us a decimal? Do you have a calculator? Negative 230 over 64.
Negative 3.59375.
3.7. Okay, so 3.7 or 3.8, depending on how you want to round it, either one's fine. Okay, so this is the rate at which the radius is changing. Notice how since it's negative, the radius is decreasing. We said that was the case because the balloon is getting smaller. Now we should have units on this. Can we think about what that might be? What is our radius unit? What is our time unit? We have dr over dt. What do you think, Anush?
Centimeters per minute.
Per minute, okay? So for volume, it was cubic centimeters. Cubic because it's a volume unit. Since it's a radius, it's just straight centimeters, meaning a distance. Okay, so there is our rate of change for the radius. We doing okay so far? All right. We are going to move on to get your supplemental sheet out, the one that had the taco cart on it. We're going to try another example. Tonight, or not tonight, over the weekend, maybe tonight if you want to do it, I want you to try page 221 and 222. Okay, we just did 220 together. I want you to try the other two over the weekend for your video assignment. All right, let's go ahead and take a look at this next question. So on your supplemental sheet, let's take a look at the falling ladder example. Okay. It says the base of a 10-foot ladder is moving away from a wall at a speed of 1 foot per second. How fast is the top of the ladder traveling when the base is 6 feet from the wall? So what I'm going to do is actually bring up a visual of this for us to see. I think that always is going to help. All right, can we watch this for a second? Did you see that word pop up? It's really quick. How fast is the top of the ladder falling right now?
8. Goes 10 meters.
That's what we're trying to figure out. So at that moment, right now, how fast is it falling? Okay? And clearly, it's falling very slowly now, but the further it gets closer to the ground, the quicker it goes, quicker it falls. So what we're going to try to do is figure out that moment, okay, that snapshot moment, that one point in time, how fast is it falling? Is that a good visual? That's what we're trying to figure out. All right, let's see what we do. So can we think of a scenario, draw a picture, and relate some of these variables together? As the ladder was falling, could you describe the shape that you were seeing change?
Triangle.
A triangle. Okay, let's draw a triangle. As the ladder was falling, can you describe any sides of the triangles that changed or were constant? What do you think, Griffin?
The hypotenuse was the only constant one.
And that was 10, right? Because that was our ladder. So the other ones that were changing were the height and the base. So maybe we'll label that B and we'll label this H. Okay, height and base. Can we identify any rates? A rate that we know, a rate we're trying to find, either one. Good, Anuj?
dB over dt, was that like -1?
Well, so the ladder's moving this way, right? So notice how the base would be getting larger. Okay, the bottom would be getting larger, so it would be +1. Okay, so it said the ladder was moving away from the wall at a rate of 1 foot per second. Away, you might think negative, but notice how this distance is increasing, so it should be positive. What rate are we trying to find? How fast is the top of the ladder? Okay, and as the ladder moved away from the wall, the top of the ladder was going down. So we know that this should be a negative answer, a negative rate, decreasing. Can we list our snapshot moment? When that word now popped up on the screen, do we have a particular piece of information available to us? Good, yeah. B equals 6. Okay, so can we think of an equation related to the geometric shape of a triangle that relates possibly all the sides together? Let's do it. All right, so b squared plus h squared equals 10 squared. Do the variables in our equation have rates associated with them? B, dB, H, dH, right? We're good to go. It's nice and even, nice and organized. So we're going to go ahead and take the derivative, plug in our values, and see if we can get our solution. So derivative of b squared, 2b, dB over dt, plus the derivative of h squared, 2h dH over dt. Derivative of 10 squared, 0. All right. Let's try to fill in what we know. Do we know the base of this triangle at our snapshot moment?
6.
That was 6. Do we know the rate at which the base is changing? 1. Do we know the height at this snapshot moment? No. Okay. Do we know the rate at which the height is changing? No, because that's what we're trying to find.
Wouldn't the height be 8?
How'd you get 8?
Well, Pythagorean theorem.
Okay, so in order for us to figure out dH over dt, we have to fill in something here. So there should be some way for us to determine that value. So at this snapshot moment, if you looked at your printed picture, we know that the ladder is 10 and the base is 6, so we should be able to figure out the height. So if we go back to the Pythagorean theorem, 6 squared plus h squared equals 10 squared. What'd you get for h?
8.
8. I like it. Okay, so even though they only give us one piece of information at that snapshot moment, we could probably use it to figure out other pieces if we have to. So we'll go ahead and fill in 8 there. All right, let's go ahead and solve for dh over dt. We'll have 12 plus 16 dh over dt. So subtract the 12, divide the 16. I think it simplifies to -3/4. So at that moment in time, when that word now popped up on the screen, the height of the ladder was decreasing at a rate of 3/4 what? Can we fill in the units of measure? Feet per second. Good. There's our related rate. We doing okay? This was just an intro. Yeah.
So how come the 3 is negative?
Like, why is this overall answer negative? Or just the 3? You subtract the 12 and then divide the 16.
Okay.
You got it? Okay. And notice how this made sense though, right? Because we said the height should be negative. The height was decreasing. Okay, everything seems to check out. We'll stop there for today. Please view the video assignment over the weekend, and we're just going to keep trying different examples, different geometric shapes of these, so that we can start to get familiar or comfortable with the process.